quantum physics. In there we have stuff like photons, electrons, all your favorite ons, but there is a problem. When it comes to light, for example, we talk about its wavelength, visible light spectrum. Going beyond visible light introduces us to microwaves, radio waves, and in all of these cases this is photons described with a wavelength. However, photons themselves seem to be a particle, and it doesn't really make sense for particles to have a wavelength. They're not a wave. So which is it? Is light a wave or a bunch of particles? So first, the experiments. We'll start with the most famous one, the double slit experiment. So, a laser, we pointed at two narrow slits. These two slits are really close together and are really small. What's going to happen to light if it crosses these slits? Well, as we all know, light is a particle. That particle is called a photon. So a laser is just a bunch of light particles, so a bunch of photons traveling in a straight-ish line. That means that when they reach these two slits, they will just get filtered through them, and on the other side you will end up with these two big blobs of light, like this. Except there's a pickle. This is what you would expect from particles, but if you perform this experiment in real life, you will see that you do not end up with two blobs of light like so, only a pattern like this. How could that be? Well, if you follow this experiment from the perspective of a single particle, you can see that it starts the laser, then is going forward, passes through the slits, and gets cast onto the wall. But this can't be what's happening. The patterns don't match. So how could our particles create something like this? Well, the answer is they can't. And so here's where the physics aspect of physics comes into play. Because when in physics you perform an experiment and it doesn't fit your model, then you need to change your model. So let's switch it from light being a particle to light being waves. Okay, restarting the experiment, except this time we start with our slits and we imagine light not as particles, only as waves. So from each one of these slits we'll have a wave. Here's the left slit, here's the right slit. Now as both of these waves interfere with each other, they create the interference pattern, which is what we actually see on the wall. So to put it bluntly, we have two theories. Either light is a particle or a wave. And this experiment states that it has to be a wave, and it doesn't make sense as a particle. Why? Because this is what you would expect from a wave. This is what you would expect from a particle, and this is what you get. Which means that it needs to be a wave. Otherwise our experiment would give us a different result. But then we have another one. So the photoelectric effect, and it basically works like this. We have a piece of metal, we shine some light on it, and it starts emitting electrons. How? Well, let's zoom in and examine it closely. Basically, we have our electrons. Now, the reason why these electrons are there contained within the metal is simply because they are stable. So basically, all of the electromagnetic attraction from the nucleus and repulsion from the electrons themselves is countering itself in a way so that on average, these electrons prefer to be in the metal rather than the outside. If an electron were to leave the metal, it would become positively charged, attracting it back. If another electron were to enter it, it would become negatively charged, pushing it away. So you can imagine it like a magnet that's attached to a metal. It will always be attached unless you give it some energy to pull it away. So if we have our magnet attached, if we hit it with a ball, this ball will knock it off, and the same thing happens for our electron. We have our electron in the metal, it gets hit with a photon, and it gets knocked off. Okay, so what's the problem then? Well, you see, when it comes to our electrons, they need a certain amount of energy to get knocked off. So just like with our magnet, if it gets hit with a tiny ball going slowly, it won't budge. The ball needs to pack enough punch to actually knock it off, and the same thing happens for our electron. Our light needs to have enough energy to knock the electron off, and once it does, the kinetic energy of the electron rises with the energy of the photon. Okay, cool. So why do we need a high Einstein for this? I mean, this seems like a simple phenomenon that even a sober scientist could solve. What's the big deal? Well, the big deal comes when we realize that with our light, the energy of the electron does not depend on light intensity, only on the wavelength. Now, I really want you to realize just how bizarre that is. What this is basically saying is that, to oversimplify a bit, an incredibly bright red room will emit slow electrons, if any at all. An incredibly dim violet room, however, would emit fast electrons with more kinetic energy, so how would that work? Well, there is one idea, and that idea basically boils down to this. Imagine our electron. We hit it with our red light like so. Okay, so our electron stays in place because that's one photon. That wasn't enough energy to move it. So we can increase the wavelength of our photon, we give it more juice, and now the electron gets knocked off. Okay, but what would increasing light intensity mean? Well, it would basically mean more photons. And as you can see, if we add more photons, they just don't hit our electron. So basically, two photons hitting the same electron is so cosmically unlikely that increasing light intensity doesn't really matter. So here you can see an intense red light and a dim violet light. Makes sense, right? If light was a wave though, it wouldn't quite make the same sense, because a wave of higher intensity would have to be higher amplitude, I guess? I mean, its wavelength is taken, it has to be, that's the only property you can change of a wave, but then why wouldn't higher amplitude result in higher energy? Well, it's because of how we do science. You should basically think about it this way. Imagine that you are just sitting with your friend, and all of a sudden your friend says, "Hey, did you know that I can fly?" I mean, that would be silly, right? Obviously humans can't fly, you think to yourself, but then your friend starts levitating. Now, if you're a scientist, then there's only one thing you can do. You have to change up your model of understanding. Clearly, your original assumption was humans can't fly, and if your friend is floating, then your assumption was wrong. So what you do in that scenario is you check for hidden strings, you check for invisible boxes, you check for any witchcraft afoot, and when you're done, if you see nothing, then you need to update your model of reality. And that is how the assumption of humans can't fly gets stricken. And so here we go back to the question of, is it a particle or a wave? You see, the problem is that the question makes a hidden assumption. That assumption is, it can be a particle, it can be a wave, it can't be both. But our experiments seem to indicate that it is in fact both. So what we do in science when we're presented with evidence that seems to counter our assumptions is change our assumptions. That's because it doesn't matter that it being both a wave and a particle at the same time seems to not make sense, because it also seems to be true. And it being true takes precedent over it not making sense. So we change them from it can either be a particle or a wave to it's a wave particle. So that's the point of the video. I just really wanted to make it as plain as I could, because in the next video of the series, I will explain how the new model of physics actually works, and from a mathematical point of view, how something can be both a particle and a wave. But that is in the next episode, because I'll be honest, I'm mostly just trying to atone for the previous explanation of quantum mechanics, which, I mean, I've just done a terrible job of explaining it. So this time I hope it was clearer on the experiments part, and I will leave the math for the future videos of this series. Yes, I really did make this video in 3 days, that's how bad I felt about the last explanation. I would like to take this time to especially thank all my patrons for supporting me, paying basically my bills. So thank you all so much. I also stream every single day a series of live streams called Charity Checkups, which I stream every single day. We're streaming for charity. Right now we're collecting money for charity Prevent Cancer Foundation. I would really recommend you join in. Even if you can't donate, still, I would recommend we have fun over there. Also, I have a Discord server in case you'd like to chat with me, and I would like to especially thank Timon for the lovely art and Tha for spreading my propaganda. Anyway, I'm gonna go now, because I need to quickly crunch my way through even more videos, and for now, that'll be it. Thank you everyone so much for watching, and have a great day. Bye.